All right, so just going to run through the 9 slides that I've put up on expected value. All right, I'm going to introduce it by way of a kind of informal example. Then we'll look at this one kind of a little bit more formally using the language and the way expected value questions tend to be laid out. A couple more examples, and then I will leave you to do some questions. So, first slide here. At Bort's Fun Fair, you can play a game in which you toss a coin with the following rules. If it lands on heads, you win €3. If it lands on tails, you win nothing. Okay, so if I ask you whether or not you'd be willing to play the game, you might ask, how much does it cost? Okay, and I've set up 2 scenarios here. Would you play it if it costs €1 to play? Would you play it if it costs €2 to play? So, like I suppose if it was class and we talk this one out, we might kind of say, right, if it lands on heads, you win €3. So heads, what's the probability of heads? It's 1 in 2. If it lands on tails, you win nothing. So what's the probability of tails? It's 1 in 2. So if it's heads, you get €3. If it's tails, you get nothing. So let's say you played this game twice, okay? And you got heads and then you got tails. All right, you'd win €3, okay? If it cost €1 to play and you've played it twice, then you'd be up €1. If you played it twice and it cost €2 to play, so you play twice, you get heads once, you get tails once, which might be what you expect to get. All right. So you win €3. It's cost €2 each time to play, so you're now €4 down. So you're losing €1 there. All right. So intuitively, we might say that if that cost €1 to play, we'd play. If it cost €2 to play, we wouldn't play. Okay, and what expected value is all about is just looking at the expected outcome on just one play. Okay, so we said that if you expect to win €3 half of the time and nothing the other half of the time, then I suppose on average, each time you play, you expect to win €1.50. Okay, and €1.50 there is the expected value of that game. All right, so on average, you expect to win €1.50 every time you play. So if it costs less than that, €1, play. If it costs more than that, €2, don't play. Okay, so as I say, that's your expected value. That's it. That's what it is. Okay, so we look at kind of different kind of examples where it's a bit longer to work out. And as I say, we'll look at the language, we'll look at the way they tend to be laid out. They always tend to be laid out in tables, these, or a lot of the time they do anyway. But that's the idea behind it. Okay, that's the idea of it. All right. So just moving on to that second slide then. We're going to learn how to use expected value to evaluate or decide if games are fair and if you should play them, and that will be with or without money involved. You'll see both types of question in your book. Other kind of financial decisions, and then maybe other non-financial things you can kind of do with it. We might return to this slide at the end and kind of review that. Expected value is the average outcome we would expect if we play the game repeatedly. Okay, so it's I suppose the average outcome on one play if we were to play it repeatedly. Okay, the reason I say play it repeatedly there is the expected value of €1.50 on that previous example. That's not, you can't win €1.50 on that game. It's either €3 or it's nothing. Okay, so it's kind of, if you play say 10 times, you might expect to win €15. Okay, if you're winning on average 150 every time. Okay, so it's the average outcome you would expect if you play the game repeatedly. Okay, but it is the average outcome of one play. All right, but like I said, it doesn't necessarily have to be one of your outcomes. In that case, it was not. Okay, on the third slide, then I have the same example we kind of looked at intuitively, where you toss a coin, you win either €3 or you win nothing. Okay, and whether or not you'd play it if it cost €1 or whether it cost €2. Okay, so what I've got here is called a probability distribution table. All right, and I'm just going to fill it in then for that example that we looked at. So if it lands on heads, you win €3. So your winnings are €3. If it lands on tails, you win nothing. So for tails, your winnings are 0. All right, and they'll refer to your winnings as X. All right. The probability of X then, well, this is quite simple. You're tossing a coin, so 1 and 2 for heads, 1 and 2 for tails. Your expected winnings then for each outcome, okay, or XPX, because that's how you get it. You multiply the winnings by the probability. So €3 multiplied by 1/2 is 3/2, or 150. 0 by 1/2 is just 0. Okay, so your expected value then is 150, which is greater than 1. Therefore, you would say, I will play this game, okay, because I'm going to win 50 cents every single time I play. Okay, if you stand there long enough, you make 50 cents every single play, you're going to make yourself a tidy sum of money. Okay, so this isn't in reality, this isn't going to be the type of game a fairground's going to put on, because if you're winning 50 cents every time, expected value 150 compared to the cost to play €1. If the fairground's losing 50 cents every time you play, they're gonna go out of business eventually, because however many times you play, the fairground plays every single time someone decides to play this game. Okay, so even if you give up after 100 tries, someone else comes along, their expected value is the same. So this wouldn't happen, okay, where the fairground would have a negative expected value. If it's positive for you, it has to be negative for them. But it's an example. Here's one which could happen in real life. So if it costs €2 to play, so your table is the same here, because if it costs €2 to play, you're still winning €3, or you're getting nothing. It's still 1 and 2 for heads. It's still 1 and 2 for tails. You're still multiplying these and get 150 or 0. But so this time your expected value, should be EX rather than EV. EV is expected value, but EX then will be what you see it called a lot. So the expected value of X, the expected result, the expected outcome on average is 150. That is less than the €2 it costs. Therefore, you would say don't play that game. Okay, so on average you win 150 every time, but it costs you €2 to play, so don't play the game. Okay, now the fairground's going to stay in business. It's making 50 cents every time, and if enough people don't do this calculation, the fairground's going to make a lot of money. But us, we know how to calculate this, so we decide no, this one is not for us. Just going to do the exact same example again, but just laying it out slightly different, basically taking account of how much it costs to play at a different stage. So the first time I ran through these, I took account of the €1 to play and the €2 to play at the end. Okay, so I compared my expected value to them. I would say that's the more common way of doing these questions or laying these questions out. But you can, if you want, take account of your €1 to play from the very start. Okay? So, exact same example as I say. So, you toss a coin. If you get heads, you win €3. But it costs €1 to play. So, how much money are you actually up? You're up €2 in that case. you get tails, so you win nothing, but it costs you €1 to play. So that is -1. You're down €1. All right. The probability, it's heads or tails, it's still 1 and 2 or 1 and 2. Your XPX then, so your expected winnings, €2 by a half is 1, -1 by a half is minus a half or minus 50 cents because it's money. So then your expected value is just to add these two together. So it's always just to add all your XPXs together. So 1 plus minus 50 cents is plus 50 cents. So you would play because the expected value is positive for you there. You're expecting to win 50 cents each time. All right. Sorry, I think I've done. Yeah, so I just realised that's slightly. Okay, so expected value plus 50 cents, so you play. Over here then, so this time it costs €2 to play the game. So if you get heads, rules are the same. You win €3, but it costs you €2 to play, so you are +1. Tails, you win 0, but it costs you €2 to play, so that's -2. Probabilities, a half and a half. XPX then, a half by 1 is plus a half or plus 50 cents since we're dealing with money. And here, a half by -2 is -1. So your expected value is 50 cents minus 1. So that is minus 50 cents. Therefore, don't play in that case, okay? Because the expected value is negative for you, okay? So you can kind of ignore how much it costs to play until the end, and then that's what you compare the expected value to. So 150 compared to the €1 to play, 150 compared to the €2 to play, and then you make that decision. Or else you can take account of the €1 and the €2 in your table, and then it's always 0 that you're comparing your expected value to. And if you get a positive expected value like I did in this one, I would play. If I get a negative one, I shouldn't play. Okay, but they're probability distribution tables. Your expected value is like your E of X is how it's written. And as I say, there's the different times in the question where you can account for the cost to actually play the game. All right, we'll do a couple more examples like that then. So yeah, so this is slide 5 in what you've got. So in another section of Port's Funfair, you can play a game in which you roll a 6-sided die. You win in euro whatever you roll. So if you roll a 1, you win €1. If you roll a 2, you win 2. If you roll a 3, you win 3, a 4, a 5, and 6. How much would you be willing to pay to play this game? Okay, so look, you'd be willing to pay the expected value, I guess, or less. So let's work the expected value of the game out. So it's a fair 6-sided die. So the probability is 1/6 for each of them. So then multiply 1 by 1/6. That's going to be 0.1666 recurring, I think. Yeah. Okay. Now I'm dealing with money, so I would probably write that as 17 cents. But I would say leave these as fractions in kind of your expected winnings. Then add them together and then change them around the 2 decimal places. Give your final answer as money, I would say. Okay, so leave your expected winnings as fractions, so you're not rounding them off too much early. Okay, so it could be it could be like a close run thing, and by rounding off too early, you could be throwing your answer off. Okay, so 2 by a 6 is 2 and 6. 3 by a 6 is 3 and 6. It'll also work out nicely doing it this way. 4 by a 6 is 4 and 6. No need to simplify here because this is just workings to get to this. 5 by a 6 is 5 and 6. 6 by a 6 is 6 and 6. So if you add all of those expected winnings up, that's your expected value. So 1 and 2, 3, 6, 10, 15, 21/6. 21 divided by 6 is 3 3.5. So €3.50. Okay, so the expected value for that game is €3.50. So you'd be willing to play if it costs $3.50 or less to play. Okay, if you were the Funfair, you would be setting the price to play that game as higher than $3.50 if you want to stay in business. But the way this question is phrased, it's from the consumer's point of view, so you should be willing to play that if it's $3.50 or less. Okay, if it's $3.50, you'll break even, fine. Okay, less, you'll win money. If it costs more than that, you're going to lose money. All right, so rational thing to do is not to play. Next slide's a very similar example. I'll run through this one, I think, because I have this one simulated elsewhere, and I will put up a video of that separately. But I'll just run through it here by hand. So a game consists of, it's the same game, but this time if you roll on 1, you win €2. If you roll on 2, you win €4. 3, you win €6. 4, you win 8, 10, 12. So it's double what you land on. Okay, the probability, the P of X, is 6 for each one. So multiply down then. So 2 over 6, 4 over 6, 6 over 6, 8 over 6, 10 over 6, 12 over 6. Add those up then to get your expected value. 6, 12, 20, 30, 42 over 6. So my expected value is 42 over 6, which is €7, which I might have expected that it's double the winnings, so the expected value is double to the previous example. Okay, so the way this one's phrased, it costs €8 to play once, should you play this game. Okay, well, €7, your expected winnings are less than how much it costs to play. So rationally, you shouldn't play that game. Okay, and then so like the Funfair or wherever this game takes place, they're basically winning €1, or they're on average they're getting €1 every time someone plays. Okay, so I'll show that in the simulation how that kind of builds up as earnings for them over time. All right. Next example I'm going to do then on slide 7 or on page 7. So you play a game with your friend. You draw a card from a deck. If it is not a face card, you pay them €6. If it is a face card, they pay you an amount of money. So there's an unknown here in the question, so a rather typical kind of twist on a question that we see in all areas of maths. What should this amount be to make it a fair game? So we're going to have some unknown here that we'll have to calculate. So what do I know? If it's not a face card, you pay them €6. So from your point of view, if it's anything other than a face card, you're €6 down. You're paying that to your friend. So from your friend's point of view, then they're up €6. All right. If it is a face, they pay you an amount of money. So that is plus X for you, and for them, minus X. Okay. What's the probability then? So the probability of getting a face card is, there's 3 of them in each suit, and there is 4 suits, so that is 12 out of 52 cards are face cards. So 12 over 52 of you drawing a face card, and then that means it's 40 over 52. Of it being anything else. Okay, so you're multiplying down then, so 6 multiplied by 40 over 52 is 4. Let's see, yeah, we might write it as a fraction then, so 60 over 13, minus for you, positive for them. It's the same calculation. And then the winnings for face is plus 12 over 52x for you and minus 12 over 52x for them. Okay, so it's you against your friend. Okay, so what you can rely on here is that the let me see now. Yeah, sorry. So we're told it's a fair game. So if it is a fair game, your expected values should be equal to each other. Okay, so if your expected value is bigger than his or vice versa, then the game is unfair. We're told in the question the game is fair, so both of your expected values must be the same. Okay, so your expected value is 12 over 52x minus 60 over 13. You'd get it by adding those together. And his then is minus 12 over 52x plus 60 over 13. Okay, so if you solve this for x, you've done the question. So bring the minus 12 over 52 over here, and you'd have 12 over 52x plus 12 over 52x. So that's just 24 over 52x. Bring the minus 60 over 13 over here, and it's plus 60 over 13. So 60 plus 60 is 120 over 13. I want to get x on its own. So let's bring, so if you bring multiplied by 24 over 52 over, it becomes multiplied by 52 over 20. So you flip it basically. So multiply by 52 over 24 when you bring it over. So 120 over 13 multiplied by 52 over 24 is 20 euro. So to make that game fair, it's 20 euro that you should receive. If it's a face card, it's 20 euro that the friend should pay out if it's a face card. I suppose looking at it intuitively, it's around about 3 times more or less likely that you get a face card, 40 compared to 40 or 52 compared to 12 or 52. So it makes sense you'd win around about 3 times as much. Okay, but that's how you deal with having an unknown kind of somewhere in the midst of the question rather at the end. All right. Grant, just going to run through then just 2 more examples as quick as I can, and then just briefly sum it up at the end and finish up then. So on to the 8th slide then. An insurance company is launching so this is just applying it to just not to games anymore, to kind of other financial decisions that you can apply expected value to. Okay, and it will be used a lot kind of in insurance. So the kind of basic ideas behind it will be used in insurance. So an insurance company is launching a death or permanent disability insurance policy. It will pay out 100,000 euro on the death of the policy holder and 50,000 euro if they become permanently disabled. Based on government statistics, each year 1 out of every 1,000 citizens die, and 2 out of every 1,000 are permanently disabled. If the company charges 300 euro a year for this policy, will it be profitable? So look, a really simplified example, but let's look at it. So what will we? Yeah, I'm gonna account for the 300 euro here during the question. Okay, and then I'll be comparing my expected value to 0. Okay, I could leave it out and then I'd be comparing with 300, but I'm gonna account for it from the start. So let's say neither thing happens. Okay, so the way it's phrased, if the company charges 300 euro, will it be profitable? So let's say we're doing this from the company's point of view. Okay, so if neither of those things happen, the company just gets 300 euro. Okay, if someone dies, the company needs to pay out 100,000 euro, but they have received 300 euro from the policy holder. So let's do 300 minus 100,000. So in the event of a death, That's a net payout of €99,700. For disability, then it is 50,000. So 300 received minus 50,000. So 49,700. All right. The probabilities then. So for death, it's 1 in 1,000. For disability, it's 2 in 1,000. For neither, then 1, 2 is 3, so 997 out of 1,000. That neither things happens. So your expected payout or receipts in each case. So I have this one up already. So minus 49,700 multiplied by 2 over 1,000 is minus 99.4. This one here, the minus 99,700 multiplied by 1 over 1,000 is minus 99.7. And 300 multiplied by 997 over 1,000 is 29910. So add those up. So 29910, take away 9940, take away 9970 is an expected value of plus €100 for the company. Okay, so on average, for each policy sold, the company makes €100. Okay, so in a very small number of cases, it ends up paying out €100,000. In a slightly bigger but also very small number of cases, it ends up paying €50,000. In the vast majority of cases, it just gets €300 in. And on average, for each person who takes out a policy, it's getting plus €100. Okay, so it is going to be profitable for the company, unless that these statistics don't hold. Okay, but this is all they can kind of base it on when they're launching the policy. And then just the last example, one where it's just not financial at all. Just because something like this came up on the exam a few years ago, and I'll give you an example like this to do in your book as well. So the ages of students in a 6th year class were as follows. Okay, so 16, 17, 18, 19, and the number of students then 3, 9, 6, and 2. So calculate the expected value of X. So this is nearly, if you pick the student at random, what kind of age would they be? Is nearly, well, I'm kind of tipping my hat at the final kind of conclusion here, but that's kind of what this question is asked. So what is E of X? So this is your X. This is the number of students. So maybe if you did your if we add probability of X to the table, there's 3 and 9 is 12 and 6 is 18. So there's 20 students in the class. So that's 3 and 20, 9 and 20, 6 and 20, 2 and 20. So then my X, PX. So multiply the ages by the probabilities. So 16 multiplied by 2 over 20 is 1.6. 17 multiplied by 9 over 20 is 7.65. 18 multiplied by 6 over 20 is 5.4. And 19 multiplied by 2 over 20 is 1.9. So plus your 5.4 plus your 7.65 plus your 1.6 is an expected value of 16.55. Okay, so maybe a little lower than I might have expected. All right. Hit that all right, did I? Yeah. All right. So what does that represent? Represents the average age of a student in the class. Okay. So 16.55. All right. All right. So like, yeah, as I said, it kind of comes up on the exam with ages. A few years ago, and there's one in the book where it is about number of siblings, but yeah, it'll be a similar idea, but just to kind of take it away, because a lot of the examples here are kind of all financial. Okay, so just to take us back just to that second slide again very briefly before I finish up. So we will learn how to use expected value to evaluate if games are fair and if you should play them with and without money involved. So without money involved, a game is fair if everyone has the same chance of winning. So if 2 people are winning and it's 50-50, play. Okay? If 4 people are playing and they each have a 1 in 4 chance of winning, play the game. It's fair. Okay? If it's a 2-person game and 1 person has a 60% chance of winning, then the game is not fair. Okay, so without money, that's what you're looking at. With money involved, then, so I suppose you play the game if it's got a positive expected value for you. Okay, you're going to win money playing the game, or if even if it's break even, you would play there as well. Okay, as I think I mentioned I do have an example where it kind of goes through the kind of that quite well, a different video, and I will link to that. All right, but I will leave you there.